Right, in a previous video, we learned that a definite integral is actually calculating the area underneath a curve from a certain x value to another x value. And when we did those, what we were doing is actually finding the areas looked great. They were shapes that we were familiar with. Now the question is going to come up, what do you do if those shapes are not regular? They're not squares or rectangles or triangles or circles or trapezoids. What we are going to be learning are some different processes that we can use to actually find the area anyway. The first process that we're going to look at is something that's called Riemann sums. At the end of this lesson, you'll be able to find the Riemann sum of a function on a given interval. All right, so let's say my problem was calculate the integral of y equals x squared, and it was like from x equals 0 to x equals 3 or something like that. And so if we drew y equals x squared looks like this. And if it's said to go from 0 to 3, what we're doing is trying to calculate that area. And my issue is again, we cannot find, that's not a regular shape. We don't have a formula to find the area of that region. So what we are going to be doing is the process of a Riemann sum. And the process of a Riemann sum is going to be breaking this area up into rectangles. So this one, it looks like it would be easy to break up into 3 rectangles. So let's say I just drew 3 rectangles. And then from what we're going to do is actually add the areas of those rectangles together, and that will give us the area. Notice it's not going to give us an exact area. We'll be finding some different ways to help us get a little bit more exact as we go throughout, but this will just at least give us an estimate of that area. Please notice in the definition of a Riemann sum, pretty lengthy and quite confusing, so I'm not going to go through this definition. There's just a few things I'd like to point out from it. The first thing that I'd like to point out is this notation right here. This notation, if you've seen it before, I think it was way back in Algebra 2. That is the notation for a sum. So sum is we're adding up rectangles. Okay, and then what we're going to do in plain English, just like I said, you're breaking an area up into rectangles of equal width, calculating the area of the rectangles, and then adding them to get the areas. So we're just going to jump right into an example. Number 1 says to consider the graphs, approximate the Riemann sum using left, right, and midpoint using the function y equals x squared in equal intervals. So we're going to be drawing rectangles, but we're actually going to be drawing them 3 different ways to see which one would give us the most accurate answer. And for ease of using this example, I'm going to change this 3 to a 6. Okay, and although it's kind of hard to see on the first 2 graphs, I can definitely tell in the third graph that there are 1, 2, 3, 4, 5, 6 rectangles. So when it said equal subintervals, there are going to be 6 subintervals because there were 6 rectangles. Okay, so the first thing that I want to just point out is which method we'll be using for each. This first one is going to be a left endpoint sum, and the reason is because the rectangles that were drawn were using the left endpoint of each interval. So here was the left endpoint. Notice the height of that rectangle would just be nothing because it starts at 0. This height was determined by the left endpoint. This height was determined going left and drawing right. Here starting left, going right. Here starting left, going right. Here starting left, going right. So notice it left some space underneath. So we should end up getting an answer that is a little bit small for our area. The next one I'm going to be looking at is the right endpoint. Here, notice for the right one, I'm actually going to start right. So if you start at the right of each one, the right determine the height, and then again go to the right side of that rectangle, go to the left to draw the rectangle. Here again, we're starting at the right and we're working left. Here, starting again right, working left to make a rectangle, starting right, working left, starting right, working left. So that's just a teeny little rectangle right there. Okay, and then our last one is the midpoint. Okay, because on this one, if you can tell, here's my rectangle right here, go right to the middle of that rectangle. Notice that's what formed the height of that rectangle, where the middle of it hit that curve. And same thing again, go to the middle here, and that's how the height was determined. To the middle again, that's how the height was determined. To the middle, and here to the middle, you can't even see it. Okay, so that's how we're going to be calculating these problems. Okay, what I would like to do first of all is, before we get into doing each of these, how wide is each of those rectangles? And the easiest way to do that, although you could probably just look at each of them, obviously it must be going by ones, to figure that out, it starts at 0 and goes to 6. So what I like to do is 6 minus 0 is equal to 6, and we wanted to separate them into 6 rectangles. So 6 divided by 6 equals 1. So each of those rectangles has a width of 1. And what I like to do, even on every single problem, no matter what, I start at 0, I go to 6. If I'm going by ones, 1, 2, 3, 4, 5, 6. There we go. There are my 6 subintervals. So that's how I start every problem, no matter what. Okay, so to get the left one, what we're going to be doing is actually calculating the area of each of those rectangles. So this first rectangle, we know that the width of it is 1 because the width of all the rectangles is 1, and the length or the height of that rectangle is actually 0 because the left endpoint, if you plug 0 into y equals x squared, you would get 0. So the first rectangle is 0. The second rectangle still has a width of 1. And then the height, if I look between 1 and 2, between 1 and 2, 1 is the left endpoint. So if I plugged 1 into x squared, I would get 1. So that is the height of that rectangle, which is 1. Okay, the next one, my width is still 1. I'm going to multiply. If I go from 2 to 3, if I'm picking 2 or 3, 2 is on the left endpoint. So if I plug 2 into this formula, I will get 4. So that height of the rectangle will be 4. Okay, and then my next one is still, the width is always going to be 1. Going from 3 to 4, 3 is my left endpoint. So if I plug 3 into x squared, I will get a height of 9. Okay, and then my next one, I know again the width is 1. Between 4 and 5, 4 is the left endpoint. So if I plug 4 into x squared, I will get 16. Okay, and then if I have between 5 and 6, first of all, the width is 1. I'm really playing with fire here because you cannot see me, sorry. Between 5 and 6, 5 is the left endpoint. So if I plug 5 into x squared, I'm going to get 25. So I get 25. So 0 plus 1. So now I'm just going to add up all the areas. And I'll put my answer up here. Oh, I think I lost my... Oh, great. Okay, there we go. All right, 0 plus 1 is 1, plus 4 is 5. Plus 9 is 14, plus 16 is 30, plus 25 is 55. So I get an answer of 55. That would be my left endpoint Riemann sum. Okay, we're now going to do the same thing with the right. And I'm going to shorten things up just a little bit for the right sum, because notice each one of these I was just multiplying by 1. So instead of having to multiply each one by 1 and show them separately, I can actually just factor out that 1 from the beginning. Now I can just add up each of the heights. So to do the right endpoint sum, going from 0 to 1, 1 is the right endpoint. Keep pushing that doggone button, sorry. 0 to 1, 1 is the right endpoint. If you plug in 1 into that formula, we'll get 1 as the height. Between 1 and 2, 2 is the right endpoint, so 2 squared is 4. And then from 2 to 3, 3 is the right endpoint, so if we plug in 3, we'll get 9. And then between 3 and 4, 4 is the right endpoint, so we'll get 16. And then 4 to 5, 5 is the right endpoint, so we'll get 25. And then between 5 and 6, 6 is the right endpoint, so if I plug in 6, I get 36. Okay, so now we're just going to, again, we're going to have 1 times whatever that answer is, and that one looks like it's going to be 55 plus 36, which will end up being 91. 1 times 91 is 91. And notice we got an answer of 55 for the left, 91 for the right. So obviously 91 was too big because we have parts of the rectangles that are hanging off. So now let's go ahead and do the midpoint. Okay, and the midpoint again, since all of the rectangles have a width of 1, we can just multiply by 1 on the outside. And now for the midpoint, this is a little trickier. Between 0 and 1, what's midway between 0 and 1? That would be 0.5. So we're going to do 0.5 squared plus between 1 and 2, 1.5 would be the one we'd pick. So we're going to do 1.5 squared plus between 2 and 3 would be 2.5. So it would be 2.5 squared plus between 3 and 4, 3.5 would be the midpoint. So we'll do 3.5 squared to get that height. And then between 4 and 5, 4.5 would be the midpoint. And then we'll square it to get the height. And then between 5 and 6, 5.5 would be the midpoint. And then we'd square it, and then we'd get our answer. Just take me a second here. I'll find out what that is. Yeah, okay, 0.5 squared plus 1.5 squared plus 2.5 squared plus 3.5 squared plus 4.5 squared plus 5.5 squared. And that gives me 71.5. And multiply it by 1, and we get 71.5. So that would be my midpoint sum. And you'll notice from each of these, that kind of makes sense that the midpoint would be in between the two, because notice I have part of the rectangles hanging out and part of it hanging in. So you can kind of see what that gives you for the area. So those would just be estimates using the left, right, and midpoint sums. Okay, another example. Consider the graph of f of x equals 5 over x squared plus 1 on the interval 0 to 3. Approximate the Riemann sum using the right endpoints of 6 subintervals of equal length. So this means we're going to draw 6 rectangles when we do this problem. So the first thing that I'm going to do is just get a picture going. When I graph 5 over x squared plus 1, it looks something like this. Okay, and we want to go 0 to 3. So we're going to stop it at 3. And we do want to draw 6 subintervals of equal length. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay, so there's 6 subintervals. We want a right endpoint sum. So what I'm going to do is start at the right, and I'm just going to go across. So start at the right, hit my function, go across, start at the right, hit my function, move left, start at the right, hit my function, start at the right, hit my function, start at the right, go left, hit my function. So you'll notice on this one it's a little different. Even though we're doing a right sum, this time the rectangles ended up inside of my figure instead of outside, and that's totally okay. So that's what my picture would look like. You won't have to be too worried about drawing the figure. We just want to kind of have an idea what's going on here. Okay, the next thing that I would like to do is figure out what those rectangles are going by. So we knew we had to get from 0 to 3. So I like to do 3 minus 0, which would give me 3. And we want to divide by how many intervals, which is 6. So 3 divided by 6 would be 0.5. So we're going by 0.5. So we're going to have 0.5, 1, 1.5, 2, 2.5, 3. So those are my intervals. Those would be each of the tick marks on that graph. Okay, so now for finding a right endpoint Riemann sum, first of all, what is the width of each of those rectangles? Since my chart is going by 0.5, the width is going to be 0.5. So we can just go ahead and put that on the outside instead of multiplying each height by 0.5. And then to get the right endpoints, I'm going to get the problem set up, and you'll have to do this too. Once we get the problem set up, I'm going to show you a very nice, easy way to use your calculator to get the answer. So between 0 and 0.5, 0.5 is the right endpoint, so we're going to do y of 0.5. Well, actually, we're going to do f of 0.5 because this function is f, plus, okay, between 0.5 and 1, 1 is the right endpoint, so we'll find f of 1, and then plus, between 1 and 1.5, 1.5 is the right endpoint, and then plus, between 1.5 and 2, 2 is the right endpoint. And then between 2 and 2.5, 2.5 is the right endpoint. And then 2.5 to 3, 3 is the right endpoint. Okay, so we'll be looking for, and even on the AP test, they want to see this setup. After you get the setup, you can use your calculator to actually get the answer. And I'm going to, again, right now, show you the easier way to do that. Okay, so we are to our calculator right now, and we're going to go ahead and put that function in our calculator. So we'll have y equals, again, we can hit alpha stat plot to get our fraction going here. There we go, so I'm going to have 5 over x squared plus 1. Okay, so I do that, and now I'm going to quit out of there, so just do a second quit. All right, now we get to use our calculator to find that answer. So hopefully I remember what I wrote down there. Okay, so they were each going by 0.5, so 0.5 parenthesis. Okay, so now we need to find f of the first one, which was 0.5. So what we're going to do is we're going to do alpha trace. And notice when I do that, notice it says y1, y1, which that's what I want because that's where my formula is at in y1. So we're going to do y1. I'm going to pick that. And then in parentheses, I'm going to put where I would like to evaluate it at. And I'd like to evaluate it at 0.5. And then close your parenthesis. Okay, and then we're going to do plus. Now I want to evaluate the function at 1. So now we're going to hit, again, alpha trace. Again, pick y1. And this time I would like that to happen at 1. Okay, ooh, and guess what I forgot? My left parenthesis. And this may seem tedious, but actually it does save time because you don't have to write down your answers in between. You can just have one final answer when you're done. Okay, alpha trace again. We want y1 again. And next we have, don't forget that parenthesis, 1.5. And then plus alpha trace once again. Oh, I don't know why that screen keeps coming up. It's driving me crazy. Okay, and then of 2. And then plus y1 again, so alpha trace. I press enter, here we go. Okay. Of 2.5. And then a plus. Hopefully you're following along, so this isn't quite so tedious for you to just watch me do it. Okay, there we go. Okay, and then 3 was my last one. Okay, and then I do need one more parenthesis because I'm closing in the whole thing. So there we go, press enter. And hopefully you got that as well, 5.114 as your answer. So we can now do, when I found that, 5.114 was the answer. Now, a lot of people are going to forget to multiply by that 0.5, but if you put it in your calculator when you start, you don't have to worry about it. And hopefully I got the right answer. So if I did get a wrong answer, if I typed something in wrong, let me know the next day after we have watched this video. All right, we're going to do one more problem, and that's what if the intervals are not equal? So notice in all those other ones, we had equal subintervals. So what we're going to do in this one, it says to use the function values in the following table and a left endpoint Riemann sum with 5 subintervals to evaluate the integral from 3 to 15 of our function. Notice we're not given what the function is, we're just given a table. And we want 5 subintervals. So what we are going to do, this is going to be my first interval. This will be my second, this will be my third, this will be my fourth, and this will be my fifth. Okay, we don't need to draw a picture because it would kind of be hard because we're just given a bunch of data points. So what we are going to do, we want to do a left endpoint Riemann sum. Notice we can't put a number on the outside because they are going by unequal intervals. So we're going to have to do just each interval separate. So from 3 to 4, the width of that interval is 1. And then I'm doing a left Riemann sum. So if I'm going from 3 to 4, 3 would be my left endpoint, and the value at 3 is 10. Okay, and then plus, my next interval is going to be from 4 to 7. The width of that interval is 3. And then between 4 and 7, 4 is my left endpoint. The y value at that point is 9. So that would be the height of that rectangle. Okay, then plus, from 7 to 9, the width of that interval would be 2. And then between 7 and 9, 7 is the left endpoint. The value there is 8. And then plus, between 9 and 13, the width of that interval would be 4. And if I compare 9 and 13, 9 is on the left, so the value that goes with 9 is 11. And then plus, from 13 to 15, the width of that interval is 2. Between 13 and 15, 13 is on the left, and the value that goes with that is 16. So from here now, it's just going to be a bunch of calculating. 1 times 10 is 10. 3 times 9 is 27, 2 times 8 is 16, 4 times 11 is 44, 2 times 16 is 32. So now if we just add those together, I'll get 10 plus 27 plus 16 plus 44 plus 32. We will get an answer of 129, and so hopefully you got that answer as well. Okay, one more thing that I would like to mention from Riemann sums, in the formal definition of a Riemann sum, there was a delta x in that formula, and the delta x is just the distance or the width of each of those rectangles. So as delta x approaches 0, as the width of those rectangles gets smaller and smaller and skinnier, the Riemann sum will become the definite integral, or the true area of the region. So the more rectangles we created in a region, that would allow us each of those widths to become skinnier and skinnier. We'd have less space either inside or outside, and we would get closer to the actual true area of that region. So hopefully now you are able to use a Riemann sum to calculate a definite integral.